I guess I should go back. First thing I want to do is acknowledge my co-authors and collaborators here. I'm the lead of this. The other three up there are actually right now collecting data. I'll talk about that later in this area that we're working on. Mr. Coffey and Ms. Hood from NOAA have been a large part of the support for this operation. Suzanne Van Cooten is the hydrologist in charge at the Lower Mississippi River Forecast Center and is the one for whom we're really developing or collecting the data. And Kevin is one of our collaborators from Altavian. All right, so the area that we're collecting this data in is called by the locals called the Honey Island Swamp. As you can see on this Google map, it's the Pearl River State Wildlife Management Area in the lower half, and it's a National Wildlife Refuge in the upper half. Put this map in here for context. This is a lot of result from Katrina having hit the coast. There was a lot of evacuation from New Orleans, moving up to the northeast, and of course many of these people didn't really think about what they were doing, and they built their houses very close to an area that once again had major implications when Hurricane Isaac hit. They built along this green area, and I'll zoom in soon to show you exactly what that is. For those of you that are familiar with more of the NASA DoD world, it's very near Stennis Space Center. Where's that laser pointer? I got it. Okay, so this is a zoom in, and the area that we're most operating in is here. This is Pearlington. I'll use that as a reference point. Some of you may have heard of that. When Katrina hit, this was kind of ground zero for the most damage. A lot of the pictures you got from the rural areas were from that area. It actually hit right along the coast here, was where the eye came across, the center of the eye. Trying to think of what other points I needed to make here before I go forward. This is the state boundary, so Mississippi, Louisiana, just to be clear here. So one of NOAA's strategic goals is a weather-ready nation. I got that backwards. So part of that is mitigate loss of life and property. This is a house that's built right along this area that you can see is not very well above ground level and very susceptible to floods. It is built raised, so this is generally where they park cars and put movable stuff in the living areas above there. This is about a quarter of a mile north of the area from which we operate, and this is right along this east bank of the river. So the issue is when Isaac came along, because they had not reflown the area or did not know exactly what was going along, coming because of all the damage Katrina had done, they predicted a flood level that required a lot of evacuation, and turned out the flood level was not that high, and it would not have caused evacuation. In particular, most of these are built to sustain a 20-foot crest. If it had been less than 20, they wouldn't have evacuated, they would have stayed put. In the more urban areas on the other side, on the Louisiana side, there's a potential for a lot of looting because of houses like this. So they really don't want to have to evacuate. Predicted a 22-foot crest, wound up with a 19.5, so there was a lot of public outcry over what happened. I'll get to the technical stuff very quickly here. So the objectives in doing this is to measure the water extent often so that we can correlate with river gauges. They've started replacing the gauges. Most all of them were wiped out all the way back up to Bogalusa, which is about 20 miles north of the tidal plain. And they've started putting them back in across the bridges. So we want to measure in dry and wet conditions, different seasons, before, during, and after storms, so we can begin to understand the hydrology through the area. Determine vegetation type and percent cover, so it's not just the location of the water edge, but it's also the vegetation type and cover, because that affects the roughness coefficients in these models that they're developing. Also, the storage. Some of it, as it rises, it'll hold water, and then it won't drain. There's actually a dirt levee type of situation, though it be only 4 or 5 inches tall. Also, how much storage and what type of storage, how it's connected. And flow rates are something we're beginning to try to get a better understanding of. My impression was water just rose, just level, and then came back down. And it turns out that because, as I understand this more, the flow may be one direction versus the other, and that indicates where the flooding may occur. All right, so our first mission was last November. We took a NOAA asset, a Puma, down there, and one of the planes we own, an Altavian Nova. We did this to try to determine, the pros and cons of each. We believed, and it was proven that the Puma was probably a more durable aircraft, but the Nova had a more appropriate payload for actually doing the mapping. Somebody asked earlier about the resolution. We get with L1 just native, like 60-inch or 1.5 meter resolution. Using updates from then, hardware, software, post-processing, we can get down to 10 centimeters without very much problem at all. So we alternated flying over the two systems over 2 days here. Just as I have a picture here in just a second, but just note we could cover about a square mile per hour with either bird. Last about 60 to 90 minutes, as was said earlier, because of the batteries. Cruise speed here, you might think the high end's the more important. It's actually the lower in some cases because you need to get overlap with these high-resolution images. Wingspan about 9 foot, length of about 6 foot, and they're hand-launched, 12 to 18 pounds. So this is a picture of an Altavian Nova, Block 3 with the wingtip off over here. Context, 2 people standing here. So as I said, about 9 foot by 5 foot. All right, and so this is in the boat, and this next one actually has the launch. So this gives you an idea of what we have to do to actually launch these things.
Got it.
Yeah, bring that down a little bit. All the way is fine. So you watch. It's going to come right at you. We were on the dock, and there it goes. So much like the one Brian showed you. This is the landing. And you need to watch right here in the center. There you go. You see it coming in. This is on a river. This is an Altavian Nova. It'll do well in water like this. It would probably not do well in breaking waves. But it works fine. We pull it out of the drink, dump the water out, blow some of the parts off, let it dry for about 5 minutes, recalibrate, and relaunch. All right, so these 2 birds, just for those of you that are not as familiar with this as some of the others are, the Puma is a DoD programmer record type of vehicle, collects video, at least the system we had, the AE, all environment. Resolution, spatial resolution, about 720 by 480. Field of view for the payload that they deploy on that. It's about 30. It is 31.5 by 21 degrees. So the footprint for both of these birds is the same. It's just the camera is oriented 90 degrees off. With the Puma, you get about 7.5-inch resolution, flying at 800 feet. With the Nova payload we were using then, about 1 inch. We've now gone to one that, as I'll mention as I go forward, we're trying to get more coverage, so we've dropped the resolution here to 2 inches, open the field of view to 60-degree field of view. I think that hits most of that. So here's kind of the comparison as far as mapping goes of what we were able to determine. This is an ArcMap image straight out of ArcMap. I think this was 10.1, the base map they've gotten it. There's one Nova flight over this area. This is actually Pearlington up here. Notice the agreement in the water edge between the base map and what the Nova was able to pick up. Now, that's 1 inch resolution, and as I said, that's a mile, square mile type of data. I believe it's actually 3/4 of a mile. We're being safe. Because we didn't want to cover everything, we were trying to do coverage as well as comparison. We've shifted down to the southwest just a little bit. We'll call this, as I go forward, a double fork. This is Highway 90, and this is an area of 2 parallel water paths. This is the Puma image. We had to extract the single images from the video and then mosaic it together. Notice the mismatches here, here, and so forth. So it does not have the best pointing accuracy. All right, so there were a couple of problems with the Puma as far as trying to move forward, though it was more durable. The pointing and accuracy, the inability of the Puma to hold nadir. When you think about what it was designed for, it makes sense. When you put a waypoint in, that's where you want to go look for the bad guy. So its camera pops up off a nadir as soon as you go to the next waypoint, and it wants to fixate on that. The other problem is it's got a gimbal lock. So even when you're between waypoints, it has a hard time holding a nadir orientation. So we wound up flying the Puma more this summer after we got a little bit more funding, got a little bit more going with it to test durability. As I said, we want a new payload. We went to one that will allow us, as I'll show you on the next slide, to get very near infrared data, 60-degree field of view, and really try to cover that whole area. So then at that point we can start comparing across season inflow from upstream when it's a different amount of water let loose from locks and dams, compare against river gauge readings so we can try to begin to understand how to correlate those and under different accumulated rain amounts. So this is we're actually flying a 550, but it's got the same spectral response. This company, Max has gone in and in a lab stripped out the internal IR filter, so we're actually able to get, it's still 3 bands, so we can pick blue, green, and red and filter out their infrared, or we can filter out down in this range and get a red and infrared signal and compare it to do vegetation and work like that. All right, present concept operations, it takes about 3 or 4 people, about 3.5 days to collect 2-inch resolution over that 25-mile square area in the lower part of that 80 square mile COA area. We can only do about 4 or 5 hour-long flights a day due to having to get out there, launch the boat, go to the location. Takes a couple of 10 to 15 minutes to do pre-flight checks, launch it, land it, dry it out, and repeat. I think I've hit most of the rest of this. Yeah, as you saw in that video, we're pretty much launching from a 20-foot boat. That's necessary because we need to get into some of these smaller sloughs to maintain visible, to keep eyes on the bird at all time. So first missions last November were up in this area. We revisited that. This whole area is what we actually were able to get in September of this past year. And as I said, we're flying right now. In fact, right now we're having FAA and AUVSI. AUVSI is coming to do a road show and filming what we're doing, and FAA decided they needed to come watch. So my crew is they're sweating heavily right now. They should have shown up about 15 minutes ago. So in that September mission, as I said, we were able to get 2-inch resolution imagery over 25 square miles in about 3.5 days. That's 16,000 images, about 150 gigabytes of raw data. We developed a geoportal, and there's the URL for it. The user interface is still under development. I just want to get it on out there. If you want to get the images, you can. We're putting individual images, mosaics of each flight, and hopefully mosaics of the whole area at high resolution. We're trying to figure out how much we can serve out. That's 4 hours, 1-day collection back in September. Future work here, we're trying to optimize the filters for the camera, trading off the RGB with the near-infrared information, trying to figure out exactly what we want to collect, optimizing white balance, water land mask, classifying these areas I indicated earlier, ascertaining the ability to determine water quality based on the remote imagery, and then sharing the data with, so it's multi-mission. People are interested in eradicating the feral hogs, counting the birds, counting the turtles, and determining the amount of invasive plant species down there. I'm out of the yellow lights on here, so I'm going to go through these fairly quickly to show you the seasonal effect. So there's winter and there's summer. You can see how much it changes. Zooming in to a point there, there's winter and there's summer, so you can see a lot more of the vegetation, how it would affect the roughness. This is really the resolution issue. This is the base map, winter, and that's what we're able to get in summer. So you can see you can actually count individual shrubs there without much problem. I've mentioned most of these people before. Cheryl Ann was here earlier this week, hydrologist working on the model, and Alan's been the operator we've worked with mostly out of Altavian. These are actually undergraduate students that are pilots and operators. So that's one image. These things are 5,000 by 3,500. You can't see every pixel there. So if I zoom in on that red rectangle up at the top, there's one of our friendly visitors in the area that we operate. So with that, I'll quit.
Okay, thank you. We do have time for a quick question if somebody has one.